What's up, guys? It's Simon Fiaz, and today's video is on AQA level chemistry paper 3, 2020. Explain how oxides of nitrogen are formed in engines. The reaction of nitrogen and oxygen, be specific, from the air at high temperatures. State why it is desirable to decrease emissions of oxides of nitrogen from vehicles. Formation of acid rain / respiratory problems. That's why, because the oxides of nitrogen will eventually lead to the formation of acid rain / cause respiratory problems. So that's why it's desirable to decrease it. Modern diesel vehicles use diesel exhaust fluids such as AdBlue to decrease emissions of oxide nitrogen. Give the oxidation of nitrogen each of these. So in this case, it's going to be +4 because oxygen is -2 times by 2 -4. In this case, well, it's going to be -3 because hydrogen is always going to be +1. In this case, that's obviously going to be 0. And then it says give the equation. For reaction between NO2 and NH3. The reaction is going to be just balancing equation, 3NO2 plus 4NH3 to form 7O2N2 plus 6H2O. And I struggle quite a bit with balancing equations. State the meaning of the term heterogeneous catalyst. The idea that the catalyst is in a different phase / state to the reactants. That won't give you 2 marks though. Then you also need to say speeds up reaction without being used up. So the idea that the catalyst is in a different phase / state to the reactants, and it speeds up the rate of reaction without being used up. Some carbon particulates are also formed in both diesel and petrol vehicles. Explain why carbon particulates are formed. Carbon particulates are formed because of incomplete combustion. State why both oxides form alkali solutions. Suggest why sodium oxide forms a solution with high pH than magnesium oxides. Why they form alkaline solutions? Because the oxide ions react with water to form hydroxide ions. And then why this sodium oxide forms a solution with a high pH? The idea that sodium hydroxide is more soluble than magnesium hydroxide, and therefore if it's more soluble, it's going to have more OH minus ions. Therefore Kw is H plus OH minus. Therefore H plus is Kw divided by OH minus. Kw stays the same, but because I've got more OH minus, I'm gonna do a number. Let's say Kw 1.0 times by 10 to the power minus 14 at, I think, 25 degrees Celsius over a bigger number. Well, then I'm going to get a smaller number for concentration of H plus, and therefore I'm going to have a high pH because pH is minus log 10 of the concentration of H plus. I think that is the whole reasoning behind it. Yeah, so it requires a bit more thinking. Given the equation for reaction between phosphorus oxide and water, P4O10 plus 6H2O to form 4H3PO4. Again, this is an equation you do have to memorize, unfortunately. I say unfortunately, but if you memorize it, and you know there's going to be at least one person who hasn't memorized it, so then you're going to get that extra mark. I think at least one. Given two equations show how this acts as a catalyst. So it's going to be V2O5 plus SO2 to form V2O4 plus SO3, and then V2O4 plus a half O2 to form V2O5. And again, you have to memorize these two equations as well. Explain why complexes formed from transition metal ions are colored. Haven't been through that. I really want to go through this one because I think I know the equation, but yeah, I haven't also gone through that. You know what? It is 3 marks though, so maybe it's not as simple as I expect it to be. Let's try it. So I just need to get the equation back up. This is obviously the transition metals. Delta E equals HV, which is equal to HC divided by lambda. Delta E equals HC. Delta E equals HC, which is equal to HV divided by lambda. H is that. V is H is that, yeah. V is, well, in this case, HC then. HC divided by lambda. Okay, so it's going to be delta E equals HC 6.63 times by 10 to the power minus 34 times by C, which is 3.00 times by 10 to the power 8, divided by lambda. This, but this is measured in meters, wavelength measured in meters, so nanometers to meters, so I'm going to have to times by 10 to the power minus 9. This is going to be 490 times by 10 to the power minus 9, and I get 4.06 times by 10 to the power minus 16 joules. Describe how calibration curve is produced and used to find the concentration iron 3 complex. Measure absorbance for a range of known concentrations. Plot graph absorbance, use concentration. Read value of concentration for the measured absorbance from this graph. The concentration of iron 3 in the solution is that. Calculate the mass used to make this. So calculate the mass needed to make this. Moles is mass over ml, mass is moles times by mr. I got the concentration. Okay, so I know what to do now. It just required a bit of work. So moles equals concentration of volume. So 4.66 times by 10 to the power minus 3 moles per d minus cube. I need a centimeters cube and mole per d minus cube, so times by 250 divided by 1000. Moles in mass for mr, mass equals whatever that is, the moles, times by the mr of iron, which is 55.8. So it's going to be 4.66 times by 10 to the power minus 3 times by 250 divided by 1000 times by 55.8, and you get 0.0650 grams. 0.0650 grams. But don't fall. I was literally about to fall for it, but then I saw the mark scheme. It wants it in milligrams. How do I go from grams to milligrams? Times by 1000. So 1, 2, 3, 65 milligrams. Name process that is prevented by cisplatin. I think I can go through this. That is prevented by cisplatin during cell division. DNA replication. I haven't gone through chloride ligands and all of that. Show how platinum complex form a cross-link between the guanide nucleotides, and I've got the cisplatin. So I've got PT, NH3, H3N, NH3, H3N. I've got nitrogen with lone pair of electrons here, nitrogen with lone pair of electrons here. Boom, going to there. Boom, going to there. Explain how graphical methods can be used to process and measure results to confirm the reaction is first order. So plot concentration against time and take tangents to calculate the gradients, hence to calculate rate, plot rate against concentration, straight line through origin / directly proportional confirms that reaction is first order. 4.5 complete table 1. They always like to ask this one. Well, it's just you just go in your calculator and do 1 over t, 1 over 3, 1/8. 0.00314 1, 2, 3, perfect. And then shift ln of k, which is the rate constant, 6.63 times by 10 to the power minus 7. And let me guess, it's going to ask us to plot a graph, which I'm not going to do. Yeah, it does tell us to plot a graph and then calculate the activation energy in kilojoules per moles per power minus 1. Plot a graph is, you do need to be able to know that skill, but you should just get something like a straight line like that, right? Then it says calculate activation energy. So I'm not going to plot the graph, I just do a quick sketch from mark scheme. How do I calculate activation energy? What is this? This is a straight line. So as it's a straight line, what's the universal straight line equation? Y equals mx plus c. So I'm going to compare this Arrhenius equation to y equals mx plus c. Mx plus c. I can clearly see y is ln k, but I want activation energy, so I don't care about that. I don't care about that. Ln a is c. I don't care about that. I don't care about that. Mx is minus ea over rt. So what's m? Well, m is going to be minus ea over r. So the gradient equals minus ea over r, and x equals t. I don't care about x. I care about the gradient, the activation energy. So if I find out the gradient, that will give me minus ea over r. Therefore, I can say ea equals the gradient times by 8.31, which is r, the gradient times by 8.31, and then divide that by minus 1, because that's minus ea equals m times by r. I want ea. And then also divide by 1000 later on, because ea is measured in joules, and look here, it wants it in kilojoules per power minus 1. So you get that, rearrange it, ea equals the gradient times by r, and obviously the negative divided by minus 1. So negative, you get rid of the negative, and then therefore ea is 109 kilojoules per mole to the power minus 1. Now I can't do question 6. Yeah. Yeah, I can't do question 6. I might try question 6.3 3 because it just looks like a half equation. But yeah, question 5 then might be the last one. It says calculate the heat capacity in kilojoules K to the power minus 1. Bomb calorimeter, there you go, blah 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 blah. Total heat capacity is that. In the experiment to calculate that, this much of hexane is that. 1 mole of hexane releases this much of energy when combusted. Heat energy release is Q equals CCl divided by T. Calculate heat capacity CCl. So CCl equals Q divided by delta T. Right. And what's delta T? A temperature change of 12.4. Perfect. 12.4. So then, obviously, it's not going to be that easy. I'm not going to use Q equals MC delta T because I can't do that, can I? No, because that's M is the mass of water. What I can use instead is delta H is Q divided by moles. And then use Q equals delta H times by moles. And I know 1 mole releases this much energy when combusted. So Q equals, well, the moles of what? Moles of hexane, the mass over the MR, times by 4154. Okay, you can see how they get a bit confusing, but it's just being so confident with these equations that you memorize that, you can just see where you need to use them. So it's going to be 4154 times by 2 divided by 86, and then that's Q. But remember, I want Q in kilojoules K to the power minus 1. Q is measured in joules K to the power minus 1. So I need to then divide my answer by 1000 and then divide that by delta T, which is 12.4. And I get 7.79 times by 10 to the power minus 3. I shouldn't get 10 by 10 to the power minus 3 though. So maybe we've done something wrong. So 4154 times by 2 divided by 86. Then divide by 1000. And then do my answer divided by 12.4. What's wrong? What did I do wrong? Oh, delta H, is that right? That's delta H, and delta H is already measured in kilojoules. So I'm using delta H Q divided by moles, so Q is delta H times by moles. Delta H is already in kilojoules, so therefore my final answer of Q is going to be in kilojoules already. So it's just going to be 4154 times by 2 divided by 86. It's already in kilojoules. I don't need to convert it or anything. So now it's doing the opposite. Like normally expects us to convert. Now it's trying to trick us into converting it. These type of questions, when in reality we don't need to convert at all. Then it says calculate the heat change for octane in this combustion reaction. And I know experiments are heated with this much of octane. Temperature changes that. Calculate the heat change. Again, Q equals CCl delta T. I want to find the heat change, right? And that is, well, if I find out the moles of octane, that's the first thing. 2 divided by 114. Then I'm like, okay, I've got the moles of that. I want to find the heat change. I know temperature changes that. So therefore, the heat change CCl equals Q never mind. So Q equals Ca Cl delta T. Delta T is 12.2. QCl I got as 7.79. Oh, right, so just use my answer from part A. Then I get that, I get Q. I want to find a heat change. Well, therefore, delta H equals Q, which is that 95, divided by my number of moles. So it's just going to be 95 divided by 2 divided by 114. 5415. Just remember to use your answer from part A. 5415, but the mark scheme said 5417, so yeah, 5417. State why the heat change is calculated from the bomb calorimeter experiment is not an enthalpy change. Pressure is not constant in bomb calorimeter. How would I know that? How would I know that? No, how would I know if he's even talking about pressure? Well, what's the definition of enthalpy change? Heat energy change. Heat energy change at constant pressure. And it says state why it's not an enthalpy change, why the heat energy change, why the heat change is not enthalpy change, because it's not at constant pressure. Pressure is not constant in bomb calorimeter. So you need to definitely memorize all your definitions as well. Question 5.4, the thermometer used to measure temperature reading, temperature change of that has uncertainty of that, calculate percentage uncertainty. So it's going to be 0.1 over 12.2, but remember, in each reading, temperature change, final minus initial, right? So I need to times that by 2. 0.1 times by 2 divided by 12.2, and then also times by 100, because it's a percentage. Times by 100, and I get 1.64%. Then it says, suggest one change to experiment that decreases percentage yield whilst using the same thermometer. Use bigger mass of fuel so delta T is greater. Yeah, use bigger mass of fuel. That should be fine. And then let me try question 6.3, because I definitely can't do the rest of them. Give a half equation for electrode in this. TiO2 plus looks like TiO2 plus to Ti solid, right? And so first thing I would be like, okay, I've got one oxygen on the left hand side, so I need to add a water molecule here. Then I'm like, okay, I've got 2 H pluses on the right hand side, so I need to add 2 H pluses on the left hand side. Then I'm like, okay, is everything else balanced? TiTi, O, 2, 2, but are the charges balanced? No, I've got 4 plus charge on the left hand side, 0 charge on the right hand side, so I need to add 4 negatively charged electrons on the left hand side. So I could do it, which is nice to know. And yeah, that's the end of section A.